So we decided that Pravin has such a long bio. He has a Wikipedia page, so I cannot do a justice introducing him. So I'm just going to say that he really needs no introduction. Thank you.
Thank you so much. Thank you for inviting me, and thanks to Demos. I was trying to recall when I first met Demos, and I think it's probably before anyone else around here. I think maybe 1975 or 74 at MIT, when Demos was my student in a class on stochastic control, I believe. And so then he went off to Alphatech. And somewhere along the line, we got together again, and then we've been working or corresponding or exchanging students or things like that ever since. And I've always enjoyed meeting Demos and having long conversations, serious conversations, as Dave said earlier. And indeed, everything that was said earlier fits Demos and also what Sanjoy wrote. So this talk is inspired by some work of Demos and another student, not Demos is not my student, but another student of mine, namely Vivek Borkar. So it's the two of them that I'm just I was reminiscing about what they did, and that inspired this talk. And Dilip Kalatil is a postdoc of Kameshwar Pula and myself, and so I roped him into it to look at literature search and to do some additional work. So that's what I will discuss. The idea is simple. So I'm considering a speculative market. There are two agents, and they can buy or sell a claim on an asset. And the asset is this black box X. If you buy it, then you get a chance to open the claim and get its rewards, which is a random variable X. And you offer to pay a particular price P. So if you buy or you sell, then you buy for P or you sell for price P, then you will get X minus P times +1 or -1, depending upon whether you're buying or selling. So that's the most basic asset pricing problem. And the price P should be such that the market will clear. In other words, everybody who wants to buy, there's somebody else who wants to sell. So the question is, what is the equilibrium price? So that's the sort of background to what I want to discuss. And in terms of a practical example that we've been working on for some time now is in the electricity market, something called virtual bidding that you may or may not know. It doesn't matter. I'll explain that. So in the electricity market, there's two markets. There's a day-ahead market. That's a forward market, sort of 24 hours in advance. You buy or sell power to be delivered the next day. And the price of that will be P. And there's a real-time market, which is at the time when the electricity is delivered. And that's a random price. You don't know the day ahead, and that's called X. And in virtual bidding, traders are allowed to buy and sell megawatts for delivery on the next day. But it's virtual in the sense that if you buy 1 megawatt in the day-ahead market, then you must agree to sell 1 megawatt in the real-time market, right? So you're balanced out. Okay? And the purpose of this whole thing is simply to shift the day-ahead price market. Okay? So you can form a demand function. The demand function will be all the buy bids, the function D of P, which is the total megawatts that people have agreed to buy for a price at least P. And similarly, you'll get a supply function, which is the total megawatts that the people have agreed to sell for at most P, right? So that forms D of P and S of P. So obviously, there'll be a decreasing and increasing function. And the price in the virtual bid price, P star or P star, will be where the two intersect, right? So that's P star. And the real-time market has a random price X. So if you buy 1 megawatt in the day-ahead market, then you pay P, and you've got to sell it in the real-time market. You get X. So your return is X minus P, right? It's a random return because x is not known. And the question is, what is the appropriate definition of this market clearing price? I mean, market clearing price itself is defined just the way I have it, but the question is that an appropriate one? So let me just do some formalism that Demos would always start with. So we'll start with a measurable space. So everything which is random is measurable with respect to that space. And nu is a measure on omega, which is really, in this agent's case, it's there prior, right? So initially, at least, I'll agree that, I'll hypothesize that all the agents have the same prior. And agent I receives some private signal, Si, right? And that's the signal that that agent is going to use to decide to buy, to sell, how much, etc. And so x, which is the return at the end of the day, and S1 and S2 are random variables, and every agent wants to maximize their expected profit. Okay? So again, the question is, what is the appropriate notion of equilibrium price, which has not been introduced, but you saw it in the earlier story. So there's something which we all do, which is the private information equilibrium. And in that, everybody's a price taker, so P is given, and they decide how much they're going to buy or sell, given their signal. So they're going to try and maximize the expected value of their profit, conditioned on what they know, right? So then agent will decide to buy or sell, depending upon the expected value is going to be larger than P, then you're willing to buy. If it's smaller than P, you want to sell. So we'll say private information equilibrium will be just some function P, which depends upon omega, depending upon what the realization is going to be, such that for every omega, the market will clear when everybody follows their own decision, right? And P is a private information equilibrium. So that's the sort of normal way in which we define people's behavior. And such an equilibrium always exists. It's just the intersection of those two curves, up and down. So let me give you an example. And this example I will follow throughout. Okay? So omega is just 9 points in here. So very simple omega. And in fact, this will be the product of the signal that agent 1 receives, which will be the column. So agent 1 means that agent 1 will know that omega is somewhere here. If it's 2, omega is somewhere here. Similarly, agent 2, if it's 1, it's in this row and that row and so on. Okay? And the payoff is defined on, or the asset value is defined on x. And it'll only take one value. If the square is red, then you get 1. If the square is white, you get 0. Okay? So that's the simple story. The distribution of omega will be determined by the distribution of S, because omega is just the product of the S's. And they're going to be independent and uniform. So the probability of any particular omega will be 1 over 9. So let's look at I'll propose a particular partial information equilibrium. Namely, take the value of conditional expectation of x as far as S1 is concerned, say agent 1 is concerned, and how much agent 2 is concerned. That's the value that agent 1 places on the asset, the value that agent 2 places on the asset, conditioned by what they know. So I'll just take the average. And it's easy to see that that will manage to, one will sell and the other one will buy. So at this point, let's look at agent 1. And supposing agent 1 has the value, observes 1, right? So knows that omega is somewhere here. Agent 1 thinks he knows that it'll be 0, but also knows that this one would be knows that you're here. So this one will take the value 1 and 2. So the agent 1 will have the value 1/3, right? Because that will be the average over there. And if agent 2 is over here, then agent 2 knows the value is 2/3. And so that'll be 1/3, that'll be 2/3, that'll divide by 2, so I get a half. So the equilibrium price, partially is given by this, right? It's the obvious thing. And you can see in here, agent 1 is willing to buy because his value is going to be higher. It's going to be 2/3. And He's willing to buy here, he's willing to buy here, he's willing to sell over there. Okay? So that will be those two squares, agent 1 will buy. So how would this be implemented? Well, you can imagine an auctioneer, sort of a classical story. Agent 1 puts his buy or sell bid. Agent 2 puts their buy or sell bid. The auctioneer announced the price P, which is just the average. And then the transactions will be made. And that's almost the end of the story. But is it really the end? So the point is that the market clearing price, P star, that half, 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 etc., it contains information about the omega which they didn't know before, right? And therefore, traders may wish to revise their trade after the fact, right? So you have, in the case of that example, where agent 1 is willing to buy, he may suffer buyer's remorse. And similarly, the seller may suffer seller's remorse. So the question is there a way to guarantee that they don't feel badly after they've made their trade? Okay? So in that respect, because they will get more information as soon as they've done the transaction, and they may regret the transaction that they made, we'll say it's not fully rational. This is just borrowed from economic terminology. A fully rational being does this infinite calculator, so knows all the implications of any action they take. So in that sense, it's not fully rational. So so P1 star supposes the first price, this partial information equilibrium. The trades are made, the market clears. Suppose now the market reopens, right? And you're allowed to redo your trade. Then each agent is asked to submit the bid again. And so now you'll get a new demand function, which will depend upon this additional information they got from the first round. And will there be a trade? And if so, that'll be a new equilibrium. And you can keep going and redoing this. Then will this sort of sequence of trades, which are sort of fictitious in a way, but you can imagine that it's done. That is, that you make an offer, but you don't commit until everybody settles down to an agreed upon price. At that point, you commit. So will this thing converge? Right? So that's the story. So that requires a sort of different notion of equilibrium than the one that we started with, because the amount of information people get has changed. So agents should be able to make rational expectations from the price. And the notion that we want should be such that at the end of the day, nobody has an interest in reopening the market. Right? So at the end of the day, everybody's in equilibrium. So let's see what happens in that particular example, what kind of information you can derive. So if you see from here and you go back, now let's take S1 equal to 2 and S2 equal to 3. So you're here and you're here. But so S1 equal to 2, so that's what agent 1 knows. So his offer will be 2/3. Agent 2 knows it's 3, so his offer will be 1/3, right? Because that's his expected value. So the average will be 1/3. The average price, the partial equilibrium, will be 1/2, and agent 1 is buying. But agent 1 knows that if that's the price and the other guy's buying, then he must be over here, because his average is smaller than 1/2. Right? So he knows that, or he knows at least that agent 2 cannot be 2/3, and therefore agent 1 can infer that this is the actual realization. Then he doesn't want to buy anymore because the value he infers that this is the actual information. So he doesn't want to buy anymore. Its value is 0, so he wants to withdraw his offer. So now he'll sell if the market reopens. Right? So you see how this thing goes, that you get more information revealed. So the notion in the economic notion is that agents are more sophisticated and that private information equilibrium is inadequate. So what is an appropriate definition? So that's the notion of rational expectations equilibrium. So the rational expectation equilibrium will be a random variable, P, that everybody knows, right? Because that's been declared. So if everybody knows P, and they know this random variable, then given P, they will know what is the set of omega that can give rise to that. Right? So that's the additional information they get on top of their private signal. So now each agent will maximize the same thing as before, given their original signal, plus this additional information derived from the price. And you go through the standard story. And so the definition of rational expectation equilibrium is a random variable p, like that, such that the market will clear at any realization. The market will clear when the agents behave rationally. And that is called a rational expectation equilibrium. Okay? So in this particular example, I won't bore you with that, but if you go through that, and I propose a rational expectation equilibrium like that. So it's half over here, and 1, 0, etc. And now let's suppose S1 and S2 equal to 3. Then agents know that P is 1/2, because that's part of the rational expectation equilibrium. So as soon as they know that P is 1/2, they know that omega is one of these things. So the agents can infer, agent 1 can infer, that S2 is either 2 or 3. And so his expectation will be 1/2. Similarly, the agent 2 goes through the whole story and determines that the expectation is 1/2, given their own signal and given the price. Right? So that's their expectation. And as you can imagine, the expected profits will be 0, right? Because demand and supply, there's no production, no consumption. So the only possible equilibrium is when the profits are 0. If one of them is getting profits, then the price will fluctuate. There'll be an arbitrage opportunity. So this is a result of Tirole and Milgrove and Stokey, which says that in the rational expectation equilibrium for purely speculative market, that's the kind of that I looked at, with risk averse or risk neutral. I assume risk neutral because I said they only want to maximize profit, expected profit, not some concave function of profit, in which case they would be risk averse. There will be no trade. The risk-averse traders do not trade because the expected profit is 0. Right? So it's kind of a surprise result because it says on the standard assumption of economics, which is that people assume a common prior, assume that nu is known to both, and Bayesian rationality, assume that they can do this probability calculus, then there cannot be any purely speculative transactions. So it raised the question as to why in the world do people speculate? Because this is what you say. And the conclusion is unclear. The conclusion is many, many things. One possibility, to which I will return with Demos's contribution, is that people may have different priors. I think it will rain. I think it will not rain. You may think differently. Yes?
Is that an existence theorem?
No, this is not an existence theorem. This is, yeah, it is not, in an equilibrium of this kind, there won't be any, right? So I'll get to the existence theorem next. But this one is not an existence theorem. It just says if there is an. So that's one issue about existence. The second issue is about uniqueness. I mean, there could be, and it turns out, A, that it exists, B, that there's lots of such equilibria. But for economists who worry about these questions at a theoretical level, it is still an issue. So one could be that the priors are different. The other ones could be people have limited rationality, so that, of course, opens up a can of worms. So then anything goes. A third may be that it is sequential, and there are other things going on. So there are many other alternatives to this no-trade theorem, but the no-trade theorem sort of stands out, right, as a contribution. So does there always exist a rational expectations equilibrium, and are there many of them? And the second question, which prompts the title of this talk, is how, if there is, how do they find it? This is related to an issue of price discovery, right? Because we said, yes, these things intersect, but how do people figure it out, right? Because there's nobody who knows the entire supply function or the entire demand function, except in that case of the virtual bid. Those bids are given, just as an aside, they're given to the independent systems operator of the electric system, and the operator receives all the bids, so can compute the intersection of the supply and the demand. So for that, I have to go to work of Vivek Borkar called asymptotic agreement. And so that's how we used to look. And that's what we are today. The day ahead and the real time. Store. Okay, so Vivek's paper had nothing to do with rational expectations, had to do with distributed estimation. So there are all these agents, they're trying to estimate a random variable x. They have different signals. How can they arrive at a consensus estimate of x? So that is the setting, but we'll see it's identical to the setting that Tirole had. So Vivek's story was that we have two agents. So at step 1, agent 1 computes his conditional expectation given his private signal and communicates that to agent 2. Now agent 2 has his own signal plus the thing that he obtained from the other one, right? So his sigma field or information is a little bit bigger. So now he computes that expectation, agent 2's expectation in round 1, and sends that to agent 1. Then, so we keep iterating the story. Then at step k, agent 1 computes his expectation given, this is wrong, that should be 1, and given all the signals that he got from elsewhere, right? And we keep going, right? This should be 1. That's his private signal. It's not S2, but S1. And the purpose of the story was to figure out what you get. And the theorem is that these expectations, step 1, step 2, step 3, etc., will converge to this random variable ai infinity. Moreover, both of the agents will converge to the same thing. Right? So that's the theorem of Borkar. And that is obviously a rational expectation equilibrium, because now they know, this will go to A infinity, now they know what that expectation is, and they have their private signal, and they come up to the same level. So that is clearly a rational expectation equilibrium. And so in a purely speculative market, the rational expectation equilibrium always exists. Now, it may be the case that me telling you my expected value, maybe I'm revealing too much of what I know, right? So the question is there something less that I can give you and we still arrive at a consensus? So this is the thing that Dilip worked out. So what he says is the same thing as before. At step 1, at the first step, both agents compute their own conditional expectation based on their private signal. They send this to the auctioneer. What the auctioneer tells you is which has a larger offer. Not what the offer is, but who is larger. Okay, so that's clearly less than giving you my full expectations. I just give you that. And so now in step k, agent k computes what they know, plus which of them had the larger offer in all those steps. Sends this bit to the auctioneer. And obviously the bids are not revealed, the individual things. And the theorem is, yes, that's enough. So they will eventually converge to a uniform price, and that will also be a rational expectation equilibrium for the same reason as before, because all this stuff converges to M infinity. And the key idea behind all of these things is to show that P is a common information. That's sort of Aumann's work. Now, there's another notion, which is the price expectation. So this is the notion coming from Radner of expectation. Okay, so rational price expectations. So suppose P is the true price function, whatever true means for the moment. But agents believe that the price function is something else, maybe Q. So what is the equilibrium notion? And Radner says the equilibrium notion is when agents believe that the price, their expectations is the same as the true price function. Okay? And that, so they understand the true relationship between the hidden information that people have and the prices that they know. Right? So that's the story. And so that's the economic connection to the equilibrium price. Now, I want to go back to the thing that Dilip did with two agents, and suppose we generalize to k agents. Right? So each agent submits to the auctioneer their and the auctioneer now computes just the median of the prices and publishes the list of agents whose bids are below the median and above the agents. Okay, the bids are not published. The theory is again that that's enough information for the prices to converge or their expectations to converge. An interesting question, however, is if instead of publishing the list, so if I give you the list of people who bid above you and below you, then you know that you're above the median or below the median, right, because you know your own. And the question is, if I only tell you that you're above the median or below the median, instead of telling you who else is above the median and who else is below the median, is that sufficient? So that's a question. Right? I don't know the answer to that. We don't know. I mean, the conjecture is maybe that's enough, but I'm not 100% sure that that is sufficient to. So it says that to get rid of these buyers and sellers' remorse, you just need something extra to. Okay, let's look at the convergence to this rational expectation equilibrium. So agent 1 starts first and assume that both signals are 3. So agent 1 knows that he's here, agent 2 knows that he's there. So agent 1 starts first, so he knows he's here, so there's 2 reds and 1 white, so his expected value is 2/3. And he sends that to agent 2. Knowing that the expected value is 2/3, then agent 1 knows this payoff function. Then he knows that agent 1 is either 2 or 3, because here his expected value will be 1/3. And this here is 2/3. And so he immediately infers that agent 1 is either, signal is either 2 or 3. He knows it's 2 or 3. He knows his own thing is 3. So he must conclude that it must be the expected value is 1/2. So he sends 1/2 to the agent. Agent 2 immediately can infer that S1, sends this to agent. So now agent 1 can infer he's either 2 or 3, and he's 3, so the value is 1/2, so he sends the value 1/2, and agent 1 does this, and they end up with 1/2. So you end up with an agreed value, which is 1/2, so the rational expectation equilibrium with this particular kind of message exchange will end up at the price 1/2. Do the same thing as before, so they're both here, but this time agent 2 starts first. You repeat the story, you end up with the value 1. So yes, so there is a rational expectation equilibrium, but what the answer will be will depend upon how this particular sequence of information exchange is carried out. So this tells you that the rational expectation equilibrium is certainly not unique, right? Because I give you an example with the same signals, and you get to different answers. So we did this. So there exists more than one rational expectation.
So if you have more than 2 agents,
Yeah.
it's going to be much more complicated.
You can get many equilibria.
Because it all
Yes. And it'll also depend upon whether 1 talks to 2 and 2 to 3, or 1 talks to 3 and 3 to 2 and 4, etc., etc.
asynchronous or not.
Asynchronous, synchronous. They'll always converge. They'll always end up agreeing. But it'll depend upon how this exchange mechanism or information exchange is developed, right? So same thing with this giving you who is bigger and who is smaller, that will also converge, and that will converge to yet a different equilibrium. So it depends upon the order. It depends upon exactly what information is exchanged, but eventually they will all agree. Now there's one other notion. So that's the rational expectation equilibrium. That's half, half, half. Then there's another equilibrium, which is the full communication equilibrium. I tell you what I know. I tell you I'm 1, so I give you S1. You're 2. You give me S2. Now we can compute. Now it's like a centralized system. That gives you, you cannot see it, but that gives you the original x of omega, right? Because omega was just S1 and S2. So that gives you yet a different equilibrium. So you can have a full communication equilibrium. You can have rational expectations equilibrium, many of them, or you can have the partial information equilibrium, so on. So there are many of these. Now, just to note, Radner also made this observation that the rational expectation equilibrium are almost always full communication equilibrium in the following sense, that if you look at all the parameters of x, right, and you look at, think of them as, in this particular case, it'll be an 8-dimensional vector because there's nine probabilities, so the 8-dimensional vector. So within that 8-dimensional space, the set of parameters in which a rational expectation equilibrium is not a full communication equilibrium, that is a zero measure set. So in that sense, everybody ends up knowing everything. But it's a trivial equation counting argument. I don't know how useful this particular kind of result is, because the actual structure of x omega depends on other things, and they may always fall into that that small, zero measure manifold. So this is this equation counting argument that everything is always full communication equilibrium. I mean, if you look around you, it's definitely false, right? That we don't know what everybody else knows, and so that's, and yet we managed to agree upon some things. Okay. So there's another notion, right, in control theory, which is consensus. That's a similar idea. People have private information. They form an estimate, initial estimate. Then they exchange the current estimate with their neighbors. So he will exchange that to these 3 neighbors. And these 3, and so get this information, take the average of it, and send it back to their neighbors. And we know that that thing will converge as well, right? That thing will converge itself. So it'll converge to B star. Then it's, depending upon the obvious properties of the graph, it needs to be connected and so forth. And so this is common in control theory with swarm behavior and stuff like that. But in this story, the agents are not rational. I mean, they're just doing mechanically that just take what you get from your neighbors, take the average, and send it off to your neighbors again. And it's possible that this thing will converge to a partial information equilibrium, right, in the absence of the auctioneer. So that's yet another notion of convergence, but doesn't have any information theoretic or rational calculus story behind it. Let me think about agents who don't know the other agent's priors. So I'm agent 1, you're agent 2. I have one prior. The new measure is new 1. You have another prior, and the new measure is new 2, and which is common. What should happen? We have to decide, what do you mean by your expectation? So the story is going to be like this. I have my measure nu 1. I know the signal that you're getting. Node signal meaning I know what it is, a function of omega. But I'll have to assume some prior on that. And I'll assume the prior that you have is the same as mine. So I assume that everybody that I'm interacting with is like me, right? So that's the orthodoxy. And that's how I will interpret your message. Similarly, you'll do the same story. You'll interpret my message according to your prior, right? So that's And that's the paper of Demos and myself. And here's how we look today. So Demos proved the following very interesting result. So it's the same setup as before, as in Borkar. I make an expectation according to, I think that you think like I do, and you make an expectation, you think like that I think like you do, and we keep doing this business. And then the result is the following, that the outcomes are divided into two disjoint subsets, A and B. And if nature happens to fall at A, then eventually we will agree. If it falls into B, then we will disagree, because I will say that you are not thinking rationally because you are making an expectation which disagrees with all my computations, right? And you will come to the same conclusion. So in that case, we will agree to disagree, in contrast to Aumann's paper, which says we cannot agree to disagree. So you said, yeah, we'll agree to disagree. But surprisingly is that we may agree even though for the wrong reasons. So I won't go through this story, but at the end of that story, we agree. And here's where agent 2's estimate will land. Here's where agent 1's estimate will land. But these values are the same, and they're different from the true, whatever the true might be, because we don't have any nature in here. So let me conclude. I may be overstating that the rational expectation equilibrium is an important concept. I mean, it is important in the study of incomplete markets, but I'm not sure that it is really important. I think it's a significant concept, and mathematical economists love it because you can play around. I mean, just the reason we love it, because you can take expectations and maxima and minima and fixed point theorems and so forth. Whether it is in practice important, I don't know. But in the economics literature, there isn't any story as to how you arrive at such a rational expectation equilibrium, and the work of Borkar and Demos tell you that one possible way in which you can do that. But the work of Demos also raises another issue, is that you can give false information and thereby manipulate the second person's expectations, right? Now you have to do it in such a way that it's convincing, right? So the thing has to, you cannot just be arbitrary, but it raises the possibility of another idea of investigation, which is how can you manipulate of a group or other people. So you can make this process converge to something which is more favorable. I come back to the virtual bids question. Suppose the market just tentatively announces that that's the equilibrium price. But now you're allowed to revise your bids. So the price will be something different. The supply function or the demand function will change because of this new information. The supply function will change because of the new information. The question is, there's a belief anyway, that the difference between P star and X will reduce. The spread will reduce. The other thing from the stuff that I just did is it says that people will arrive at a similar valuation of that real-time market, which is the X. Therefore, the demand function should become more elastic as you repeat, and the supply function should become more elastic. So that's a question that may be worth study. And another thing is there any notion of the minimal amount of information that you can provide and achieve consensus? So I will stop by that, except for happy birthday to Demos, and thank you very much.
And then finally, I'll talk about Cloud RAN, which is a disruptive architectural concept that sort of throws everything up in the air with regards to where the functionality is placed and how it interacts.